Hello, and thank you for your interest in this e-talk. I will be talking about the concentration versus virial mass relation of dark matter halos, and especially focusing on strong gravitational lensing. This is work that has been done with a number of collaborators you see there, and I especially highlight Dominic Lyer, who has been pretty much doing all the hard work. So this is a very introductory slide where we show mainly the fundamental importance of the connection between dark matter halos and galaxies. So on the one hand, we have the dark matter that provides a structured evolution, the backbone, if you want, of the way galaxies evolve. But then on the other side, galaxies provide the so-called baryon physics, where the processes going from gas into stars operate. And most of the observables are related to the baryon content. So it's always a complication, basically trying to use observational data to derive the elusive dark matter. There are three main pillars in terms of the observations of the derivations of the presence of dark matter. The first one is through dynamical modeling. So the idea is that we produce a velocity map, a distribution of the motions of the stars and perhaps the gas as well. And then we use various dynamical models such as solving Jeans equations, Schwarzschild modeling of orbits. We impose some level of symmetry to make the problem more tractable. And eventually we end up getting the gravitational potential and the density distribution. Another option is looking at the hot diffuse halo gas that emits in X-rays. So there you produce observations in the X-rays to derive the luminosity and temperature profile of the system. You make another types of assumptions, for instance, assuming hydrostatic equilibrium, and in the end you end up getting equations that give you the distribution of mass in the system. Finally, the one that concerns this talk is gravitational lensing, where we make use of chance alignment of background sources whose light rays are being bent as they traverse the gravitational potential of the lensing galaxy. By solving the lensing equation allows us to produce a surface density of the system. So this is what we will be working on here in this talk. So the modus operandi here would be, on the one hand, we have the lensing system. So here you see the source plane, the lens plane, and here the observer. And the idea is that we solve the lensing equation rather than using a parametric system. We use a totally non-parametric approach where we pixelate the lens plane. So the surface mass contained within one pixel would be free except for the constraints imposed by the lensing equations and a few other small constraints. So I refer you to this paper by Williams and Saha, where the details of pixel lens are laid out. Then we have a look at the image, the photometry of the system, and then we apply population synthesis modeling that allows us to transform light into stellar mass. And we get things similar to what you see here for the Einstein cross. So here, for instance, in blue, you see the profile of the mass contained within a given radius. You see the characteristic butterfly shape of the uncertainty that is minimum at a region close to the so-called Einstein radius. And for the stellar mass, from the photometry and population synthesis modeling, we have the red dots here. So automatically we have a way of estimating the amount of, if you want, stellar component and dark matter in our system. If we extend this analysis to many other lenses covering a wide range of masses, we get something similar to this result that you can see here, this animation from the paper of Lyer and ourselves in 2011. And the idea is, first of all, you can, for a given lens, you can open up your aperture and measure the amount of stellar and dark matter, lensing matter, and then you get rid of that to produce the dark matter. And then you see here the comparison between the lensing mass and the stellar mass. So as you're opening up your aperture, of course, the contribution of dark matter is more dominant. But not only that, if you go towards more massive system, you see the dots move more vertically, which means that basically you have a more dominance of dark matter in more massive galaxies. So this is a manifestation of the high mass branch of the so-called abundance matching plot, as you see here, the connection between the halo mass and the fraction between the stellar mass and the halo mass. So one more step you can do is try to come up with an estimate of the concentration, if you want the gradient, the amount of mass contained in these lenses. We're doing this as a first approach, we're doing this a la CAS, so you know this non-parametric approach done with photometry. And what we do is we basically get the fraction between the radius that contains 90% and 50% of the mass. That could be either the lensing mass or the stellar mass. And we plot this as a function of the total mass. And you can see that for the stellar mass, you see these gray open circles. The concentrations are relatively high, and the more massive systems have higher concentration overall. I mean, there's an amount of scatter. But clearly, for the lensing mass, the systems become less concentrated as they are more massive. This is a representation of a well-known concentration virial mass relation, and it's fundamentally connected with the hierarchical buildup of structure, in the sense that the more massive systems will have virialized at later times. So through the collapse at later times, that means overall the densities are lower, and then the concentration will be lower. So this is a very fundamental aspect. If you want to go in more detail here, what you need to do is go to a parametric approach. So in this case, what we did was fitting the data to an NFW profile. We note here, these are the fitting points, and we note that the lens only corresponds to a part of the extent of the halo, a relatively small radial range, so we have to be aware of that. But another word of caution is when you're using abundance matching, basically going back to this slide, if you're trying to use, let's say, the mass of a given system to infer the amount of dark matter, and from there basically try to add one more point in this fit, sometimes it may be okay. So this is the point that we expect for abundance matching for this specific lens, and this is the equivalent for this lens. So you can see in this case it's okay. Abundance matching is fine, but here it is not. And this is important to make sure that we cannot always apply these types of constraints, mainly because abundance matching is purely a statistical approach, where you're connecting the mass function of dark matter halos from simulations with the stellar mass distribution of galaxies. So this is the main figure that we are concentrating on in this talk, which is, you see the concentration virial mass relation. Our results are shown in this pink points with blue confidence levels, and then we also include the data from X-ray work done by Buot and collaborators, where basically the systems that are being considered are groups and clusters of galaxies. So we see that our results provide a nice extrapolation towards lower masses, in the sense as expected that the more massive the system is, the lower the concentration. But the important key point here is this intriguing difference between our results and the predictions from numerical simulations from, for instance, the work of Macho et al. Other papers provide similar types of results. In this realm of masses, their concentrations are substantially lower. So we need to understand this. We need to know what is causing this mismatch. So the result was there, it was presented some time ago, but then we went back to it and tried to see whether the systematics of our approach was to blame. The easiest way is, let's try to present simulation data exactly in the same way as what we are doing with the lenses. So the idea would be, we go to the Eagle simulations, we extract a given snapshot, let's say let's say a zero redshift snapshot, and then we basically get all the dark matter and stellar particles from galaxies within the same type of, let's say, stellar mass as the lenses. We produce arbitrary 2D projections, and we pixelate them exactly in the same way as what we have done with PixelLens, and then perform the same fitting procedure to see whether our systematics is to blame. So that's the way to go here. Try to explore whether the concentration virial mass relation that we get produces indeed a problem with regard to the simulations. And these are the results that were recently presented in a letter to monthly notices. You can see our results for real lenses appear in red, and in blue you see the results from the Eagle simulations. And once more you see that at the given, at fixed value of the, let's say, the virial mass of the lens, the Eagle simulations once more provide lower values of the concentration. So the problem is there. You cannot blame systematics associated to our modeling approach. Not only that, it's not that the concentrations are lower, also you can see that the slopes that you get are substantially shallower. So if you use this simple approach, it's simple fitting for the concentration virial mass relation, the slope that we get for the Eagle sample is this one here, minus 0.08, which is consistent with the result done with a numerical simulation. So Machio et al. Give minus 0.11, so it's within error bars, it's consistent. Whereas the lens sample gives a substantially steeper relation. So this is something that we need to understand. So before I finish with the conclusions, I just want to plug this interesting result regarding lensing, which is coming from a serendipitous discovery of a citizen science project, Space Warps, where we found a lens that has a tremendously large Einstein radius for arc seconds. We found that there are not many, let's say, group or cluster members associated to them. So in principle, this is potentially a fossil system at quite a significantly high redshift, given that fossil systems are mostly known at lower redshift. The interesting thing is when you do the lensing analysis of this object, you get a lensed mass of 10 to the 13, so it's a group type of system, but then the stellar to dark matter ratio sits high above the abundance matching relation. It's going back to the point that I mentioned before. These objects perhaps are very special in the sense that they are very efficient at converting their baryon content, their gas content, into stars. So I just leave this one there, and I will finish with the conclusions. So in this final slide, I show the conclusions. On the concentration versus virial mass relation, we find that lenses over galaxy scales have concentrations that are significantly higher than expected from simulations. And this is work that was already presented in those two first papers that I show here, 2012 and 2016. Recently, what we did was subject exactly the same type of methodology to a number of simulations from Eagle. The methodology was now exactly the same, and what we find is that the simulated dark matter halos have concentrations that are always consistently lower than the real lenses. So in order to explain this, a number of options are out there. One is a systematic of lenses. Perhaps lensing systems intrinsically are very special. Perhaps they are at the high concentration tail of the distribution. The other option is there could be a problem with the models, although this is unlikely since simulations perhaps are not so trustworthy regarding the baryon physics, the subgrid physics, whereas the understanding of the dark matter, the collisionless material, should be better understood and better described by the numerical simulations. However, at the level of the models, perhaps the baryon physics, for instance, the adiabatic compression type of argument, could mean that the baryons are driving this compression, this increased concentration. And another option is, of course, the chance of self-interacting dark matter. So changes in the dark matter physics might be able to produce these types of results. So I just wanted today to show you these results that I think warrant more attention and more analysis to make sure that the simulations and the observations are made consistent. I would be very happy to be in contact with you. Here's my email address if you want to get in touch with me. So thank you very much for your attention. Bye-bye.